The purpose of the report is to demonstrate the phenomenon of decay process initiation of non-radioactive isotopes, that is artificial radioactivity under condition of a glow discharge plasma with deuterium and protium, using the example of a change in isotopic and elemental composition of impurities in palladium and nickel cathodes, and to discuss the possibility of understanding of this process as nuclear chemical reaction initiated by non-equilibrium high-energy electrons. The installation of a glow discharge is shown on slide 3. The discharge chamber consists of a double quartz tube cooled by running water with cooled electron holders and flanges. The installation is described in detail in nearly works. Slide 4 shows the discharge gap zone in the deuterium plasma on the palladium. On the left, conditionally stable discharge, on the right, unstable discharge. It's possible to see more intensively luminal spots are seen on the palladium sample, as well stronger luminous rays in the discharge gap and discrete luminous seals in the lower plasma ray. Slide 5 demonstrates pulsed discharge in deuterium with palladium. On the right, we can see unstable discharge. On the left, we can see single pulse of the stable discharge. It is possible to see the current on the left, maximal current in pulse 4 ampere, and on the right we can see a set of pulses with a current amplitude several times higher, current maximum more 20 ampere. On the sixth slide, we can see pulsed discharge in hydrogen on nickel samples. On the left, stable pulse discharge with maximum current 1/2 ampere, and on the right, unstable pulse discharge, formation of additional pulses of high intensity with maximal current 4 amperes. Mass spectrometric elemental and isotopic analysis of our sample was carried out with using ICP-MS mass spectrometer with an inductivity coupled plasma. The scanning area was selected with dimensions of 6 by 2 square millimeters for palladium and 3 by 1 square millimeters for nickel. The number of measurement pulses related to each isotope was summed up from 15 measurements, which were registered during scanning of the selected area. The table 1 shows the isotopic ratios in percent, red number for the basic element palladium, and sums of pulses, black numbers, from one of the several experiments. The standard deviation for palladium isotope sum of impulse was not more than 1 to 1.5%. the magnitude, larger numbers of pulses produced during ICP mass spectrometry analysis by isotopes of the main element palladium after deuterium plasma irradiation and glow discharge can be considered as consequence in the high defectiveness of the palladium structure formed during the deuterium ions irradiation. They increase into 7 to 9 times yellow row. We are preliminarily interested in the effect of a decrease in the initial content of impurity non-radioactive elements in the studied cathodes after 40 hours in plasma of a glow discharge. We would like to pay attention of the remaining fraction of the lead isotope, yellow row. The remaining fraction of lead isotope contain much less than 1% in comparison with original foil. Data of the table 3 illustrates the decrease in amount of platinum in the palladium cathode after irradiation in the deuterium plasma. Only 1/3, approximately 30% of the amount of platinum isotopes remain in palladium after 40 hours of exposure to glow discharge plasma, yellow row. The isotope tungsten in palladium cathode after 40 hours in deuterium plasma. I would like to pay attention. Tungsten are absent in the original palladium foils. Impurity tungsten appears in palladium foil after 40 hours of treatment in the deuterium plasma. We believe that the appearance of tungsten isotopes can be obtained by the interaction of the deuterium-containing plasma with platinum isotopes, both initial and formed during initiating transformation from impurity lead isotopes. Table 5 illustrates the change in ratio of isotope before and after irradiation in the protium plasma. Table 5 shows that mass spectrometer records an increase in number pulses of all nickel isotopes by a factor 40 to 60 after irradiation in hydrogen plasma of a glow discharge, yellow row. This fact can be considered as a consequence of high defectiveness of the sample structure formed under irradiation with protons. Table 6 illustrates the decrease in amount of iron isotopes in the nickel cathode after irradiation and protium glow discharge. It's pay attention to disproportionate change in isotope ratios of impurity iron in the nickel cathode. The content of isotopes ratio after before iron 54 increased approximately 3 times and other isotopes decreased. Table 7 demonstrates the very significant decrease in amount of zinc in the nickel cathode after irradiation protium. The remaining proportion of zinc 40-64 isotopes was less than 5.5%. Other isotopes contained less than 1/10 of the percent yellow row, but the fraction zinc 64 moilite isotope increased by a factor 2, while other isotopes they decreased is amount occurred 25 to 90 times. One can see an increase in the percent content of the light isotope as the content of iron 54 increased equal by factor of 3, and zinc 64 increased by a factor 2. Table 8 shows the change in the kappa isotope ratio. An increase in amount of the lighter isotope kappa 63. The remaining amount of kappa isotopes were less than 1/10 of a percent yellow row. Table 7 to 8 reflect the effect of reducing the content of impurity isotope iron zinc kappa in the nickel cathode. It is paying attention to be disproportionate changes in the isotope ratio of impurity iron zinc in the nickel cathode and lead in palladium. An increase in the percent content of the light isotopes are registered. The content of iron 54 increased equal by a factor 3, and zinc 64 increased by a factor 2. The increasing of more light isotopes means that the physical properties was not the reason of this changing, preferred evaporation, atomization. Possible process and corresponding reactions are discussed in 7 to 9 reference. The studies carried out have shown the possibility of initiation the transmutation of initially non-radioactive isotopes of impurity elements into palladium and nickel under low energy effect in plasma. In the analysis mass spectra, the most changes in quantitative composition of impurity elements are orders of magnitude less than content of the basic elements palladium and nickel. 3. The attention of the unproportioned quantitative isotope composition change of impurity elements with the increased percent of light isotopes and decrease of more heavy isotopes. The full set of these results can be understood on the basis with the concept of the initiating role of non-equilibrium electrons of high on the chemical scale energies of the order of 3 to 5 electron volt, which interact with the deuterium and hydrogen and plasma with formation of neutral, d-neutron-like and neutron-like metastable particles participating in nuclear chemical reaction with impurities and basic elements of the cathode.